All right, this is chapter 1.3. We're doing notes number 6, and we're going to start looking at the graphs of functions. So first of all, I want to recall the definition of a function. The kind of shortest way we can define a function is saying a relation for which, here's the important part, every input has exactly one output. Visually, we can look at this as the vertical line test, because think of what that's saying. Every input, which is like an X value, has exactly one output, which is typically a Y value. So let's just say we just sketch any sort of graph. I'm going to do something that looks kind of polynomial. Say that's my f of X. No matter where I pick an X value on the graph, that input has one output on the graph and no other. Same here, same here. So you can think of this as like I could draw a vertical line, which represents an X equals value anywhere throughout the graph. And the vertical line will only intersect the graph of f of X at one point. So that's a visual representation of every input has exactly one output. So we can't use the vertical line test as a justification on our AP test. So can't use on AP exam. However, you can do that kind of quickly in your head to decide, is this a function or not? And then when you're justifying on the AP test, you'll say every input has exactly one output. So I want to practice using Desmos a little bit. So this says use a graphing utility to view the graph of the equation. So I'm going to primarily teach this class using Desmos. If you prefer your graphing calculator, that's okay. But you'll need to come to me individually with questions on how to use it. Desmos is so much more user-friendly, I would say. So I just went to desmos.com, open our graphing calculator. On test day, you'll have one on your school Chromebook that you can access when you need to use it. And I'm just typing in, so let's see, use a graphing utility to view the graph of the equation and determine if y represents a function of x. So this is just to practice. I like to use the keyboard a lot. Shift 6 gives you an exponent. So you're not clicking around here and typing stuff in. Minus 2x plus 3. So here's what that graph looks like. And yeah, I would say that passes the vertical line test. And maybe you didn't need to see an example of that graph. Hopefully you knew, oh, this one's quadratic. It looks like a parabola. So I know that it would pass the vertical line test. But just to practice with Desmos, that's kind of how we do that. All right, so this is a function because every input has exactly one output. Now, you might get sick of writing that, but the reason I want you to write it each time is so that you remember what to write. That's an easy point to get if they ask you this on the AP test. So here's the nice thing about Desmos versus having a graphing calculator. If I am trying to graph x squared plus y squared equals 16 in my graphing calculator, I have to solve it for y and generate two different equations because there'd be a plus or minus involved. But for Desmos, we can just type in what we see. X squared plus y squared equals 16. Maybe you remember this from conic sections in Algebra 2. But yeah, that's the equation of a circle. So a circle does not pass the vertical line test. There are all kinds of outputs or inputs except for -4 and 4. Every other input has two outputs instead of exactly one. So I'm going to write that this is not a function. And there are a few ways you could word this. You could just say every input has two outputs, or you could say multiple inputs, or I usually just say something like some inputs, because it's not technically all, -4 and 4 are not. Some inputs have multiple outputs. Sometimes we give examples, like for example, we have 0, and when you put in 0, you get plus or minus 4. All right, and then our last one. Now this one, I would not know just what the graph of that looks like. Let's just get rid of these other two here. So we definitely need a graphing utility for this. You can type in 1 divided by. If you type in the letters SQRT for square root, it will pop up a square root. I don't like clicking in here, especially if you don't have like a wireless mouse or something. It can get tedious to click in this keyboard and find what you need. So I try to do keyboard stuff as much as I can. Here's a weird looking graph. But does it pass the vertical line test? It's hard to tell that this is like going vertical here. It looks like it's just like, oh, it just stays at the same vertical value, but Desmos can't really, just like our graphing calculators, can't get too accurate with this. But if we were to type in, let's call this f of x. If I were to type in, instead of -5, -4.9, I get this value. If I were to type in, I did 4.9, whatever, 4.99, I'm getting a higher value. Put a few more nines in there. See how it's getting bigger and bigger and bigger. So this is not just like a vertical line. It is approaching infinity. So you're not getting the same output for multiple inputs here. It's just very steep, and Desmos has a hard time tracking it, just like our graphing calculator would. So this does pass the vertical line test. There are asymptotes at plus or minus 5, but within its domain, every input has exactly one output. So this is a function. Every input has exactly one output. And why do we put exactly in there? Why can't we just say every input has one output? The exactly sort of implies that there is only one, or one unique output. It's another way that we sometimes say it. So you need the word exactly in there. Okay, increasing, decreasing, or constant functions. So I think that I already have pictures maybe that I left on here for you. Did I do that? I thought that I left these in here for you. So let me just so that I have the same picture. Do a quick little copy, paste that out here, drag it over. Okay, magic. All right, so if a function is increasing, here's an example of an increasing function. And you can see the x coordinates are a and b. So if a is less than b, just meaning a is to the left of b, that implies that f of a should also be less than f of b. And that's because your point that's on the left should be lower than the point that's on the right. And with a decreasing function, the opposite is true. So a is still to the left of b. If a function is decreasing for any interval, now I have x1 and x2 here. I really should have like a and b. I don't think I fixed that for your notes. Then the opposite would be true. So f of a would be greater than f of b because the y values, the outputs, are decreasing. And if you have a constant function where still a is to the left of b, it's going to be a constant function as long as f of a is equal to f of b. They're on the same exact level. Now, I point this out just because these are our official AP definitions of increasing, decreasing, and constant. We may just have to identify sections of a graph that are increasing, decreasing, or constant. So let's just go ahead and look at these. These are already graphed for us. This x cubed graph, even though it looks like it's a flat line right here, think about x cubed. You have 0, 0. If you put in 0.1, you're going to get a different value than if you put in 0.2 or 0.3 or negative 0.1. So this is constantly increasing here. So this graph is increasing across all of its x values, negative infinity to infinity. When you're answering this, by the way, you use x values or inputs, and you only use parentheses because we would consider any point at which a graph is changing behavior from increasing to decreasing or whatever to not fall into either category. So, all right, so this first graph, it's increasing here and here. You have to trace this from left to right. So this graph is increasing from the x coordinate negative infinity because it goes on forever up to -1. And then it also increases from positive 1 to infinity. You can use a union symbol here. I don't think our AP test is too particular about that. I'm not going to count off if you leave off your union symbol there. And then here's a decreasing section. So decreasing from -1 to 1. So remember not to use the y values there. There is no constant section. And then this third graph is a piecewise function. You can see it's a line, then a constant, then a line. So the first line is increasing. That's going from the x coordinates -infinity up to this x coordinate, which is 0. And then we have a constant section. The constant section spans from x coordinates 0 to 2. And then finally we have a decreasing section, and that's going from 2 all the way to the right, so 2 to infinity. So you'll never use square brackets here, only parentheses. Looking at functions that change from increasing to decreasing also lets us look at relative and absolute extrema. Sometimes on our AP test or the calculus AP test, instead of saying relative extrema, they'll use the term local. And instead of absolute, they'll use the term global. So you need to know both. A function has a relative maximum at any point where the function changes from increasing to decreasing. That makes sense, right? This is a relative maximum right here, this point. A function has a relative minimum at any point where the function changes from decreasing to increasing. And the relative minimum would be right here. Relative max and relative min do not have to be the highest point, not always highest or lowest. It's just where the function is changing behavior like that. If a function is changing from constant to either increasing or decreasing, that's nothing. That's not a relative max or min, because you've got to be changing from increasing to decreasing or vice versa. So think about this picture here. So let's say I go from increasing to constant, and then, I don't know, constant to decreasing, something like this. Maybe that's my piecewise function. So none of these are relative extrema, because think about it. What makes this a relative max? It goes from increasing to constant. Why would this be a relative max versus the point next to it or next to it or next to it? It's got to be the highest or lowest point relative to that little section of the graph. Or again, definition is changing from increasing to decreasing or vice versa. There's nothing about constant. Now, an absolute max or min is the actual highest or lowest point. So these can only occur, it's got to be on a closed interval, meaning they're telling you to look at x values from -10 to 10, not -infinity to infinity or something like that. So on any closed interval, they can either happen at the end points of that interval. So if I say, take a look at a graph from -10 to 10, -10 could be where a relative max or where an absolute max or min is, or +10. Or it could happen if there's a relative extrema. Maybe that is actually the highest point. All right, so on the graph below, label the relative and absolute extrema on the interval -2 to 4. So pay attention to the graph because you're given more than just -2 to 4. So here's -2. I'm just going to kind of mark off on the graph where that is. And 4 is about here. So we're only looking at this section of the graph. And because that's a closed interval, there has to be, this is a continuous function, there has to be an absolute max and an absolute min. So let's start there. Let's start with the absolute min. Oh, you know what? It's kind of hard to actually label these. So let's label it on the graph. So this right here looks like the lowest point, and it happened at an end point. If this section of the graph dips down lower, then that would have been the absolute min. And it looks like the end here is also the absolute max. Neither of those are relative extrema because the graph isn't changing from increasing to decreasing there. We do have multiple relative max and relative min points though. So anywhere the graph changes from increasing to decreasing, which is here and about here, those 2 points are both relative or local max points. And then this point where we change from decreasing to increasing, and same thing here, both of those are relative min. Concavity, this is a big thing that we focus on in pre-calculus and calculus. So the graph of a function is concave up on the intervals at which the rate of change is increasing. So this is an important relationship that you need to memorize. Rate of change, remember, means slope. So if a function is concave up, the rate of change is increasing. So concave up looks like this. It's sort of like a bowl shape, I think of. And then concave down looks the opposite, looks like that, kind of like a hill. That's where the rate of change or the slopes are decreasing. So what do we mean by that? The rate of change is increasing, the rate of change is decreasing. So let me just, I'm going to list out some slopes that are increasing. So let's say we have slopes. Let's say our slopes are, let me list them in an increasing order, -2, -1, 0, 1, 2. And then let me just flip that around. Let's do slopes that are decreasing. So we'll start them at 2. 2, 1, 0, -1, -2. So I want you to sketch in these little slopes, and they're going to be like slopes at, sort of like tangent slopes at points on a curve. So first we're going to sketch in the slopes, and we'll kind of see if that curves around. So sketch a slope that's -2. So maybe like, it's got to be a negative slope and it's got to be fairly steep. So something like that. That's -2. And then -1 would be negative but a little less steep. Maybe like that. A slope of 0 is like a horizontal line. Slope of 1 should be sort of a mirror image of your -1, but just going positive. Same with slope of 2. So can you see how this forms that curve of a concave up graph? So if you can say you have a concave up graph, you know for sure whatever the slopes are, their numbers are decreasing. So it's not about steepness. It's just about the numbers are, increasing. I said decreasing. And then the same thing would be true if we start with a slope that's the highest slope and then we go down to the lowest number. So start with a +2 slope. Let's start it down here. Something positive and steep. And then a little less steep, but still positive. And then 0. And then -1, -2. So that's forming a concave down shape. So anytime we see a section that's concave down, the slopes might be different numbers, but whatever the slopes are, if we were to list little tangent slopes or find slopes between any 2 points from left to right, they would be decreasing numbers. All right, we're going to use Desmos for this. And this is important, a good skill to have. You need to be able to obviously type an equation into Desmos, but also you need to be able to find that graph. It's not always easy to see the graph that you're looking at. So let me clear out all this stuff I had on Desmos here. Okay. I want to first type in this equation. You can type it in as you see it, which is kind of nice. So you can call this R of t equals, and then just be careful about typing it in exactly as it looks. I put in the zeros just so that it's easier for me to spot check. Plus 1.428. Okay, so do a quick check here. Make sure you typed everything in right. So 0.03 t cubed minus that t squared plus 6.587 t plus 1.428. Now, see how it gives you this little domain here? I can see this graph just fine. It's not extreme, but I want to look at the window that they're telling me. So here's kind of a nice thing, and we're going to use this skill a lot on our AP test anyway. To be able to zoom fit and get the section that they want you to look at, you can either, well, I want to do it like this. I know that you can restrict the domain of the graph over here, but I don't think that's necessary. I want to add a table. And let's put in those 2 endpoints. So the inputs are 0 and 20. And we don't have to calculate numbers here because we called this R of t. We can type in R of 0 and R of 20. Okay, it'll see how it kind of marked that point off for me. And then here are two things that pop up. This is regression, which we'll deal with at a different time on a different problem. This is zoom fit. And so see how it kind of zooms out for me an appropriate amount, and then I can see the part of the graph that I need. So here's the section of the graph that I need between these two red points. Okay, so what was the question? It says, the rate of people entering a subway on a particular day is modeled by the function r. So r is a rate of people measured in people per hour, and it's got this equation. T is measured in hours since the subway began service for the day, so it runs for 20 hours. Based on the model, at what value of t does the rate of people entering the subway car change from increasing to decreasing? So this is just asking, r is the rate of people entering the subway car. So where do we change from increasing to decreasing? So let's take a look at our graph. Increasing to decreasing is right here. On Desmos, just click near where that relative max is, and it will find that point in gray for you. So they want the time, not the y value. So the time is the x coordinate, 5.505. All right. So our answer is D. So it's not difficult. A lot of the calculator problems are quite easy on our AP exam. We just have to know what they're asking and kind of how to perform that in Desmos. Okay, points of inflection. A point of inflection is just a point where the graph changes concavity. So let's look at something like, give yourself a curve that kind of does, I don't know, one of these. It's got to do like an S-type curve. So this section is concave up. And then at some point in here, just kind of eyeball where it happens, the graph switches to concave down. That's what I mean by changing concavity. So this would be a point of inflection. Sometimes I'll abbreviate that, POI. All right, so take a look at this AP problem. It says here's a graph of f. The figure shows the graph of function f. The zero and extrema for f are labeled, and the point of inflection on the graph is labeled. Let A, B, C, D, and E represent the x coordinates at those points. Of the following, on which interval is f increasing and the graph of f concave down? So remember, concave down looks like this, but this would be the increasing section. So just this half of it. So to me, that looks like this section, right? A to C is concave down, but we only want the increasing part. So A to B. All right, and then here's a problem, part of a problem that we're going to see on our free response question number 3. We have 4 free response questions. They are all laid out so far. They're all laid out exactly the same, so we know exactly what to expect. They just changed the functions and equations and stuff that they give us. But let's suppose that we already have these points for F through P. So I just want to label them. Well, actually, no, I don't want to label all of them. So say we have these points. Refer to the graph of H, which is this, in part A. The t-coordinate of J is T1, and the t-coordinate of K is T2, so J to K. So let's go ahead and write down the ordered pairs for J to K. I'm just taking them from here, J to K. On the interval T1 to T2, which of the following is true about H? Now, H is just saying the graph or the Y values, or the outputs, or however you want to think about that. So we really only care about the fact that J goes from negative 0.5 up to K, which is 0. So what's true? Are those values positive or negative, and are they increasing or decreasing? So we're going from negative 0.5 to 0. Those values have to be negative, so we can cross out the positives. And are they going up or going down? This section of the graph is going up. So negative and increasing. Describe how the rate of change of H is changing on this interval. So this is always a question about concavity. So remember back here, let me go back. When the graph is concave up, the rate of change is increasing. When the graph is concave down, the rate of change is decreasing. So we're literally going to write that. We just have to identify the correct scenario. So again, we're looking J to K. That section of the graph is concave up. So here's how I have to write this. H is concave up on T1, T2. So the rate of change is, what did we say? Rate of change is concave up, increasing. It kind of goes together. So H is concave up, rate of change is increasing. Those are the two important things that you have to write for that. All right, that finishes up today's notes. We're going to practice more of these free response number 3 questions and some other graphing questions. Please come into office hours or send me an email if you have any questions.